Welcome to lecture 27 on risk management and insurance. In the last lecture, we used the option pricing model to calculate the optimal insurance premium. In this chapter here, we provide now some background material to that. I'm following here the book by Hull, Options, Futures and Other Derivatives. It's an excellent book, and if you plan to work in financial markets, then that's a book that is really worthwhile to buy, and you should actually read in that book. I'm only using here chapter 14 and chapter 15. When you buy the book, you have to be careful. It must have exactly this title. Hull wrote two books, a very easy introductory one, and then this here more advanced one. And the two books have very similar titles. So make sure if you buy the book that it has exactly this title, otherwise you get the wrong one. Now, an Ito process, equation 1 gives you an Ito process. So we have here the change in a variable x, and that change in a variable x depends on a deterministic, has a deterministic part, and it has a stochastic part. So here we have the drift A. So in each small time period, x maybe goes up or down by a times dt. So that's the drift, and that's deterministic. And then here we have the stochastic part. The stochastic part again depends on the random shocks dz, which follow a so-called Wiener process. The Wiener process, remember, those are independent random draws. So the covariances are 0, independent random draws with mean 0 and standard deviation 1. And then naturally, the standard deviation of 1 would not apply to all different types of assets x. And so we multiply here with a scaling factor of the standard deviation. That's this b here. So the change in the variable x, or maybe an asset price x, has the deterministic part. We have this drift A, and we have here this stochastic part, which comes from random draws from a Wiener process. And we multiply here by b. That's a scaling factor for standard deviation. Now here, we do it in a more general way. So the A can be a constant, but it also may depend on x and t. So it may depend on x on itself, and it may depend on time. Same thing here is a scaling factor for the standard deviation. It may be a constant b, or it may be actually a function of the level of x and a function of time. Now we already used the geometric Brownian motion in the last chapter. So here I write it down again. Here the drift is mu x. So you see the drift depends on x, but not on time. So the drift there depends on x, but not on time. Same thing here for the scaling factor of the standard deviation. It depends on x, but not on time. So it depends on x in the geometric Brownian motion, but the parameters then is actually constant across time. Time does not matter. So that's the geometric Brownian motion that we used before. So let's now assume a variable x follows an Ito process as given in equation 1, And let's now consider the function g of x. So what is the process of g, of the variable g, if the variable x follows an iter process? So that's a purely mathematical problem. But it also has an interesting economic application here. You see, G may be the price of a derivative security that depends on the price of some underlying asset X and maybe time T. So that's why we speak about derivatives. A derivative security depends on the price of an underlying asset. It's derived from the price of an underlying asset. So we have here this important application to us. But naturally, you just can look at it as being a purely mathematical problem. X follows iter process. What is now the stochastic process of G? Now let's use a Taylor series approximation for a function now here with two variables. We have two variables. We have x and t, and we will just approximate this function g with a Taylor series approximation. So we have here the first order terms, dg to dt, dg to dx. Then we get here the second order terms, dx squared. You also would have a dt squared. And then you also get some cross products, dx, dt, and so on. And you would also have the higher order term, and third power, and so on. Now, a Taylor series approximation for a function with two variables is quite unwieldy. It looks very unwieldy. And then actually, if you have three variables, it's getting even worse. What you do then is actually you use matrix calculus. But we don't have to do it here, because in stochastic calculus, actually all those higher order terms are zero. They vanish. So we will have, we can approximate the change in G just by those two first order terms and then this single second order term of X. And all the higher order terms that we have will actually be zero. So that's what the Ito equation is about. Now you can show this with this small table, which applies to stochastic calculus. So I have here this dz, and there's a dz. That's from the Wiener process. So if you have dz times dz, what you get is dt. That's what this table shows. If you have dt times dt, you will get a zero. And if you have the cross product, dz times dt, then you will get the zero here and naturally also here. Now this table I do not prove. You will find it in books that explain you stochastic calculus. Naturally this has to be proven. But this is now very convenient for us. So let's apply those rules here and let's calculate dx squared. You see here we need the dx squared. So let's calculate that. Yeah, the x from equation 1 is just the geometric priming, the Ito process. I use here an Ito process. So that's coming from equation 1. I just take the Ito process and now assume that the a and the b's are constant. To make a simple example. So I have here a dt, b dz. And you just multiply this out. So you have the first item here squared, the second item here squared, and then you have 2 times this in the middle. So that's just algebra. You just multiply out. So do this squaring. And then you have dt squared here. So dt times dt, that gives me a 0. So I can plug in here a 0. And then the same, dt times dz. So cross product, t times dz. That gives me a 0. So again, I can put in here a 0. But here at the end, dz times dz, that gives me dt. So for this dz square, I must write dt. So I have here 0 plus 0, and here I have b squared times dt. So that's what left over. Now when we go to the higher order terms, dx to the third power, okay, that's dx to the second power times dx. So I can just take here dx to the second power, I can take this from above here. b squared dt, that's dx squared. And then I multiply again by dx, which comes from the Ito process, a dt plus b dz, that's a drift, and that's a stochastic part here. Multiplies that stuff out. You get this here. And then dt squared, that's again 0. And the cross product is also 0. So actually this higher order term, dx3, will be 0. And then actually dx4 is also 0, because dx4 is dx3 times dx, and dx3 is 0, so dx4 will be also 0. So all higher order terms then actually will be 0. So the dx square is not 0, but then the higher order terms are 0. Now this here with dt, already the t square is 0. That's from the table. T square is 0. So naturally, d to the third power is also 0, and so on. And the cross product here, let's look at this one. I have dt, again for the dx, plug in from the beginning, equation 1. So that's equation 1, dx is a dt plus b dz. I take a and b now constant. So plug in for the dx, multiply it out, and again you have a 0 here, and you have a 0 here. So all the cross products also will be 0. So we can substitute this now into equation 4. So only thing that we have to substitute in is here's this for dx squared. We put this in here. So for the dx squared, you substitute in here. And for the dx, you take equation 1. For the dx, you take this here from equation 1. So substitute in here for the dx, substitute here for the dx squared. And then rearrange, and you will get this here. It's direct algebra. It's very easy to do. And you get the Ito equation. Now, in commerce classes, and sometimes students really worry about this equation. It looks somewhat complicated, but it's actually not. You see here, again, I have a new drift term. What I have here in the bracket, that's just a number. That's a new drift term. And the volatility here, that's also just a number. So this is just a new scaling factor for the dz, for the random draw. And this here is a new drift term which applies to dt. So what I have here, a function g of xt of an Ito process x is just another Ito process. So if you begin with an Ito process x, that the function x, a g of it, is also an Ito process. So here we just get the new Ito process now for g. We have a drift, that's just a number here, times dt. And then here, that's a scaling factor, there's a new scaling factor for the standard deviation. That's also just a number, times dz. So if x follows Ito process, so the function g of x also follows an Ito process. And importantly, both Ito processes depend on the same random shock, dz, on the same Ito process. So here I'm getting the same dz. So if I have here in the original x here, let's say we have here a strong positive shock, which puts upward pressures on the x variable, then I will have here the same strong positive shock, which will put upward pressure now on the g variable. So the derivative security price G depends on the same Wiener process as the underlying asset price. And that's now will become very important. Just looking ahead a little bit, but then we will discuss it again later on. Since the derivative and the underlying asset price depend on the same stochastic process, so then we can actually really construct a risk-free portfolio by just holding the right amount of a short position in the derivative and a long position in the underlying asset. You see, both are actually dependent on the same shock. And so if we just buy the correct amount here as a short position and the correct amount here as a long position, then the two positions will cancel out. But this we will see later on. Let's now make an example. First, let's do two examples here, and we can go back to chapter 1. Let's go back to chapter 1. Now we had this arbitrage condition. We saw that the forward price on some asset equals the spot price times e to the power here is interest rate. We apply this interest rate. You can look this equation up. We explained the forward price, okay, how it's related to the spot price in the market. And it was an arbitrage condition. Now let's assume the spot price, S, follows a geometric Brownian motion. Now I take now a specific Ito process. I work now here with a geometric Brownian motion, but it's an Ito process. And let's now calculate all those terms that we need into Ito equation. So df to dt, time matters up here. You get this here. That's this first derivative. And you naturally know why the minus r is here. Okay, so that's again the chain rule. You see I have the t up here as a power. So I have here a minus rt. So you write this down again when you take the first derivative, but then don't forget to multiply with the derivative of the power. So that's coming from the chain rule. Now the derivative is regard to s matters. So that's not just the e to the power. And the second derivative with regard to s, that one is 0 because the s is no longer here. There are no further changes here when s changes. So we get here a 0 for the second derivative. So mu s, that's the a. So that's the a here of the geometric Brownian motion, that's a drift. And the b, the its Ito equation, will be the sigma s. That's the drift. So you plug all this into the Ito equation. For example, here we have the dg to dt. So that's now here, the g function is naturally the f function. So that's becoming this expression here, this first derivative. So the g function is now, here's the f function because we deal here with the forward market. So right here, this first derivative, then when this second derivative here turned out to be 0, so this entire stuff here becomes 0. So here's this last term here becomes 0. And so A here, so that's a drift of the geometric Brownian motion. You see, the A is the drift of the geometric Brownian motion. Here we have the A. So write mu s. For the A here, I'm writing mu s, and so on. So you just substitute in. It's very straightforward. And then remember that s times e with a power, that's just the f. That's the arbitrage condition. S times e just gives me the f. So I can use equation 10 and I can simplify. Just write here f. Now also here, write just f. And again here, s times e. You can also write f. And here's an action you can factor it out. So you get this here. So if the underlying asset here, if the spot price here follows a geometric Brownian motion, then the forward price on it will also follow a geometric Brownian motion. We have here also geometric Brownian motion, but we have even the same, volatility here, the same scaling factor for the standard deviation. We have a new drift, it's mu minus r, so we have to subtract the interest rate here. The drift before was just mu. And we have again the same shock. So if you have a very strong positive shock in the spot market, which drives up the forward price, here a strong shock in the spot market, which drives up, which drives up the spot price. Okay, strong shock here, it drives up the spot price according to the geometric Brownian motion. So then we have the same shock here, strong positive shock, which will drive up the forward price. So we have this relation between forward price and the spot price, and the Ito equation shows, okay, how we can derive that. Now here, let's look at the purely mathematical problem. So I have here a variable s, could be again the share price, and then let's take again the function g of s, and yeah, okay, time does not matter here, so time will drop out. But g naturally depends on the s. So I take the logarithm here. So the g function is just simply the logarithmic function. G of s will be the logarithm of s, and the time then actually really does not matter. So what is the stochastic process of the logarithm of s if s follows a geometric Brownian motion? So let's assume the stock price follows a geometric Brownian motion. Then what is the stochastic process of the logarithm of the stock price? And again, you determine those terms that you need in the Ito equation. So we get dg to dt is naturally 0 because time does not matter. Then dg to ds, that's just the rule of calculus for logarithm. You just get 1 divided by s. And the second derivative gives you a minus 1 divided by s squared. So that's naturally the case because here 1 divided by s, you can write for this s to the minus 1 power. So the minus comes down, and you have now a second power. And then again, the drift comes here from the geometric Brownian motion, and also the scaling factor, the a and the b, okay, will be as before. Put this now into the Ito equation. So for example here, the first term is 0. Remember here, this derivative here with regard to time is 0. So when you go here to the Ito equation, then here's this first term will be 0. So plug in again everything. Substitute in, also substitute in for the A and the B here from the geometric Brownian motion, and that's what you will get. Now here, the logarithm of the stock price will now follow a so-called arithmetic Wiener process with a drift here and this volatility. So if you take a semi-logarithmic graph, if you plot share prices in logarithm, then you actually will show the percentage changes. You see here, that's the drift in percent. We have to subtract here something, but that's usually a very small term. And here's the sigma, that's also the volatility measured in percent. So we have now here a percentage change. And that's why the semi-logarithmic graph actually works. If we go back here to the geometric Brownian motion, remember here's a drift is actually determined as a percentage of the level of the variable x. Mu is a percentage. And the same thing, the volatility is expressed as a percentage of the level of the variable. So here then becomes dollar, percent of a dollar term, percent of a dollar term. So we have here dollar, and then here we have the dollar change. But the mu and the sigma, that's a percentage rate. And so here, when you do this, so when you take now the share price, when you take the logarithm of the share price, and you plot that. So here you have now a percentage change, because that's percent, and this is a mu, is also percent. And then we have here this small term that we subtract. Now, this drift mu is often called the expected return of the share, but really the correct expected return would be mu minus this small term here. Now, that's also a little bit further explained in the Hull book. Okay, that was the lecture of today. Thank you.